Hello everyone, I'm Faiyaz SIddiquee and today I will talk about orbital velocity. Let's begin. Okay, so before we begin, let's actually understand what orbital velocity means. So let's say we have a planet here, or it can be any celestial object, and we have another object which is orbiting this planet. Now, what do I mean when I say orbiting the planet? What I mean is that, say, it's orbiting in this direction, and after some time, it is here. And if we say that this distance is r, the distance from the center of the planet to the object is r, here, after some time, when this object is here, this distance will also be r. Or in other words, this is a circular path. This orbit is a circular path. Now, as this is a planet and this has a mass, this will pull the object, the planet will pull this object towards its center with a mass, say F. Now, if this object has no velocity in any direction, what will happen is this object will start falling to the ground, falling towards the center, and it will stop when it reaches the ground. But we don't want this. We want this object to orbit the planet. So let's actually give this object a velocity. Now we will discuss about what this velocity will be in terms of equation later on. But if this velocity is not strong enough to dominate over this F, what will happen is eventually this object, due to its velocity, it will not fall straight to the ground, but it will spiral and eventually fall to the ground, because its V is not enough to dominate over F. So, in a certain velocity, what will happen is this object will always keep on falling, and it will always keep on falling and falling, but it will actually never reach the ground, and so it maintains this distance r from the center of the planet. And that velocity in which it will maintain this distance r, or it will orbit, is called the orbital velocity. Okay, now let's try to understand what the equation, or what this orbital velocity will be in terms of equation. Now, this is our planet, and this is our object. And this is traveling at velocity v, and this distance is r. Now let's say during its orbit, after a very small time, we will call that delta t, this object comes here. Now we say that this delta t is very small. So we know that this orbit of the object is circular. But even though it's circular, as this delta t is very small, so it's after a very short amount of time, this will actually be a straight line. So we can consider it as a straight line, and we'll call it here d. We'll call it d, and also this distance is r. So we know that the distance traveled by an object is actually this the velocity by which it travels times the time it takes. So this comes from the definition of velocity, which means the distance traveled in a certain time. So we know that this d is equal to this velocity times delta t, the time it takes. Now see that this, we can call this v1 and we can call this v2, and this will actually not be the same. But I have said earlier that, well, this cannot change, or else if you change the velocity, that will not be a specific velocity that will keep it in orbit. But actually what happens is, here the direction of the velocity changes. See, here this is directed here, and this time it's directed here. So the direction of the velocity changes, and as the velocity, it's a vector quantity, so the direction matters. So due to this direction, there will be a change in velocity, but the magnitude of the velocity will be same. So we can write v1, and this is a vector quantity, the magnitude of v1 and the magnitude of v2 will be the same, and we can call that v. Now let's do a bit of geometry, and that will take us to the final answer of what this v might be. So let's consider two triangles. We can see that this triangle has formed, in which these two sides are r, which is the distance from the center of the planet to the object, and this one is d, and we will write that as v times delta t. And now another triangle has been formed, which is this one. This is v1 and this is v2, and as I've said, there was a change in the direction of velocity, so we can say that this one is delta v, caused by the change in the direction of the velocities. Now see, if I draw this one again, and this one will be r, and this one will be v1, this one will be v2, and this will be the center of the planet. Now see that, now notice here that this will be a 90 degree, because if this is not perpendicular to the ground, then this velocity will be directed elsewhere, and say if it's directed to the surface of the planet, then it will just fall to the planet, or it will fall to the planet here or here. Okay, but that's not what we want. Okay, we don't want that. Or even if the velocity is directed elsewhere, it will just go off and not be able to orbit the planet. So therefore it must be parallel to the ground or the surface, so that it never actually touches or gets directed towards the surface. So we understand this very important fact, that this angle is 90 degrees. So as this angle is 90 degrees, this will also be 90 degrees. And now in this diagram, we can say that this is 90 degrees and this is 90 degrees. Now let's extend this v2 here so that it intersects v1. Let's call this angle alpha. Now as this is 90 degrees, this is also 90 degrees. As this is a straight line, this is 90 degrees. So this one must be 180 degrees minus 90 degrees, which is 90 degrees. Now from we know that the interior angles of a quadrilateral, this is a quadrilateral, will be 360 degrees. 360 degrees. So alpha plus, now see, let's define this angle which it has covered, this angular distance theta. So this will be theta, the angular distance it has covered in delta t time. So this will be theta. So we can say that alpha plus theta plus this will be 90 degrees and this will be 90 degrees, which is 180 degrees, equals 360 degrees. Or we can say that alpha plus theta will equal 180 degrees, or alpha will be equal to 180 degrees minus theta. Now see that in this triangle, as we have extended this V2, so this angle here is actually this angle, and this angle, see, this is a straight line formed by V1, so this must be 180 degrees minus alpha. And what is that? That's 180 degrees minus 180 degrees minus theta, and that's actually theta. So we can say that this is also theta. And now we have something interesting. You can see that in this triangle, this is theta, and in this triangle, this is also theta. So let's just draw this one, which will be R, and this one will be V times delta t. This one is V times delta t. Over here, and this is theta. And for our other triangle, this will be P1, this will be P2, and this will be delta V. And this is also theta. Now observe something. Both of these triangles are isosceles. Both of them are R, and see, this length actually represents the magnitude of V1. So we know that the magnitude of V1 and V2 is equal, and they're equal to V. So this is also equal. So we have found an isosceles triangle, and we know that this isosceles triangle will be equal. The base angles of an isosceles triangle are equal, and this will be 180 degrees minus theta divided by this, divided by 2. And so is this, and so is this angle, and so is this angle. So we can see that if this is triangle 1, if this is triangle 1 and this is triangle 2, triangle 1 is similar to triangle 2. This is because all the angles are equal. So this actually comes from the angle similarity theorem. So as these two triangles are similar, we know that we can write the ratios of corresponding sides of similar triangles, and we can write them as equal. So they're equal. So the ratios of corresponding sides of similar triangles are equal. So we can say that here, let's consider this one and this one because they are corresponding. So we can say that delta V from triangle 2 divided by V times delta t is equal to, we can consider any other side. Let's consider R and V1. This will be equal to, so this is taken from triangle 2, so this V that will be here will also be from triangle 2, and this divided by R, so they are equal. And okay, this will be V1. Now this actually represents the magnitude, so here I have also written that as a magnitude. So you can say that delta V divided by V times delta t is equal to, so this is V and this is R. we have said earlier that this magnitude of v1 and v2 are equal, and we have defined that as v. So we can actually say that this delta v by delta t is v squared over r, and we have actually found that this is actually the acceleration, right? Delta v times delta divided by delta t. This acceleration is equal to v squared over r. This is actually what is called the centripetal acceleration. So this is our last step. Now here we will include two formulas, which will be Newton's second law and the universal law of gravitation. So we know that Newton's second law says F equals ma. So this is if this is an object with mass m, and a force is applied to it, which causes it to accelerate at acceleration a. So the relation will be F will equal to ma. And also from the universal law of gravitation, we know that the attraction force between two objects, if this is mass m and this is mass little m, and this distance is r, will be equal to the gravitational constant g times m times little m divided by r squared. So we can see that both of these equations refer to F, or the force. So we can say that, well, as F will be equal to F itself, so ma will be equal to gm by r squared. And what is m? This is actually the mass of the object which is orbiting. So this mass will be m, mass of the object which is orbiting the planet. So we can cut out the m's. So here, see, the mass of the object which is orbiting the planet does not affect the velocity at which it needs to travel in order to orbit. So this a, as we have found out, is v squared over r. So this m does not affect the v. It will be equal to gm by r squared, and this will be equal to, this is just r times r, so we can cancel out one of the r's, and we have got our equation. V squared will equal to gm over r, or therefore v will equal to root over gm by r, and this is our equation. So here, this is the orbital velocity. The interesting thing is that from this equation, we can see that if this is a planet with mass m, and if there is another object at height r from its center, there is a specific velocity which will keep that object orbiting around the planet. So there is a specific orbital velocity at every r from the center of the planet with mass m. And one thing to note here, if you consider this one as the radius of the planet, and then this will be, and this as separately as the height of that object, you have to include that v will equal to root over gm over this whole distance from the center to that object. So that will be r plus h. Hope you have liked it. Thank you.